So welcome everyone. We're very happy to do this first inaugural conferences and that Laurent Polidori has accepted to do them for the project, the collaborative project in environment and society. This is a series of 2 lectures. So the second part we follow next Monday on the 8th of March at the same time. So just remember that, the same link that you have received. So Laurent Polidori is an expert on remote sensing and geodetic sciences. He was the director of CESPIO, which is one of the main French research labs in the field, professor of CNAM, and currently he's left France to take up a position as professor at UFPA and UFRA in Brazil. So I won't, this is a very short introduction that will not make you justice, but I want to leave you the floor, Laurent. Thank you very much again for having accepted this. And just a practical detail for everyone who just joined. We'll look at the chat box and save the questions for the end, unless it's a clarification question, and then we'll ask, we'll interrupt the presentation, basically. Because I think you're all unmuted, so ask your questions on the chat, please. Okay. Thank you.
I hope everybody can hear me. First of all, thank you for this introduction, and thank you for inviting me to make this presentation. Well, of course, I'd rather be in front of you than in front of a screen, but I'm afraid to have no choice, and I will try to do my best today and next Monday to give a presentation with some illustrations on the topic of spatial remote sensing and social geography. I have been carrying out research for more than 30 years mainly in South America, but also in France and elsewhere, on the remote sensing and its applications. And I want to stress that social geography is not really the application that is most familiar to me. However, I have been involved in many projects, and I've been working with, in partnership with many people from different social sciences, demography, epidemiology, history, archaeology, and so on. So that I think I should be able to give an overview of the potential and the limitations of remote sensing for what I could call here social geography. And just to clarify the words, spatial remote sensing consists in observing the Earth's surface with sensors on board satellites, and more specifically sensors measuring the light and any kind of radiation, and organizing the measurement in images. This is why there will be many images in my presentation. And I call here social geography in a very intuitive terms as describing and understanding how human societies are distributed on the surface of the Earth. First of all, I would like to give some figures to introduce to illustrate the heterogeneity of human density on the Earth's surface. First, what is the total area of continental surfaces? It's about 150 million square kilometers. What is the total population of the Earth, worldwide population? It's about 7.5 billion people. So with these 2 figures, we can compute very easily that the average population density is 50 people per square kilometer, including desert and polar regions and so on. And similarly, we can compute that the average available land area per person is 2 hectares. It means that we all have 2 hectares at our disposal, but obviously these 2 hectares are not used in the same way everywhere. And this means that the average values are not significant, and we should rather see how human societies are spatially distributed. And then the question is, how can remote sensing describe this spatial distribution? We could think of seeing people. However, I would say immediately that seeing human beings from satellite is very limited and in fact not very interesting. We can count people in the demonstration. In this case, it's not satellite, it's rather a drone, a multi-rotor drone. We can also use high-resolution satellite images, for instance, to search a lost navigator in the middle of the ocean, but this is not social geography. This kind of application has typically military inspiration, and this kind of work is typically transferred to the civilian world to answer some very specific and operational questions. So Another approach is to tell you that in the past years, I would say the past 20 years, remote sensing Earth observation satellites have been able to detect human beings from altitudes of 300 to 1,000 kilometers altitude of the satellite. And we can see this, for example, in this image of the QuickBird satellite. This area is Paris La Défense, and you can see that each small dark point is a person. So it's possible to see people. And this has given the idea, and just to take an example, the acuity, the visual acuity of the satellite able to see a person from several hundred kilometers height is the same as a human eye, which will be able to see a bacteria on the ground. Okay, so it's not a detail, it's very impressive. The resolution is very, very high. The problem is that this has given the idea that social applications of remote sensing would need a high resolution. And in fact, this is an illusion due to two main limitations. The first one is spatial resolution. I said that it was very, the improvement was very important. However, the resolution, which is the ability of the sensor to discriminate two point targets close to one another, the resolution is hardly better than 1 meter, so that the size of human person is very is not sufficient for real to implement this approach. And the other limitation is that most people are not visible from above. We are all mainly inside buildings. For when we work, we sleep, we eat, we are with alone or with friends. We are most often inside buildings, so that it's not possible. Most people cannot be seen from space. So this is a clear limitation. So the relevant approach, and this will be the start point of my presentation. The relevant approach is to use remote sensing to highlight the traces left by nature and society on the Earth's surface. So if I may illustrate this by one first example, this is an image from one of the Spot satellites with a 5-meter pixel size. This is an important criterion over a rural area of Japan. And this image is clearly showing, on the one hand, natural traces like rivers and coastlines. On the other hand, human traces like agricultural plot boundaries or communication axes. You probably wonder about this strange red color, and I must indicate that this image is a color composite where the red channel of the screen represents the infrared wavelength, which is very sensitive to vegetation, and this is often the case in the images I will show. So this is the way satellite images can be used to highlight traces. This is really the relevant approach to implement remote sensing as a tool for social geography. And my presentation will illustrate the variety of traces, which I would say, like messages, is written in different languages, and also the variety of sensors which are able to read these different languages, because each sensor will see some traces and not others. For instance, the famous nightlight mosaic provided by NASA, based on the images of the GMSP satellites, is a way, among others, to describe the spatial distribution of human societies on the Earth's surface, with its biases and its limitations that I will comment later. And I just put here below two examples, the United States on the left and France and part of Western Europe on the right, two examples of regions which are both densely populated and rich enough to switch on many lights. We can also see ephemeral traces. For instance, on the left, we have a place with gold washing in French Guiana, so gold mining in river sediments. So each, you see the trajectory of a river, and each bright point is a small decantation basin. So I'm not a specialist in gold washing, but a specialist could tell you, could describe for you how this activity is being implemented. And on the right, we have here a refugee camp in Syria. So I say these are ephemeral traces because they can stay here. I will say they remain visible for 1 day, 1 week, maybe 1 month or 1 year. It depends, but they are not supposed to be permanent. And if the satellite is not present, is not available at the right period of time, maybe this information can be lost. Just to be more complete, I would say that observing human traces on the Earth's surface is not the unique case of this approach, the unique case of observing traces to detect and understand some different phenomena. Here in these images, I show on the left 2 radar images of the surface of Venus, of Moon, and the Moon. Obviously, these traces are not human, they are natural. And on the right, you have an image of the channels on the surface of Mars, the famous canali that suggest the presence of water in the past, and that made people believe 1 century ago that maybe they could have been a civilization on Mars. And on the bottom line, I just wanted to show the examples that also animals can leave traces on the Earth's surface, from left to right, the trampling of cows creating a new channel. In the middle, a cornfield partly destroyed by a locust attack, locust criquet in French. And on the right, the moles, the moles is top in French. They dig galleries underground and they open mole hills in the grassland. So these are examples that not only human societies create traces on the surface, and we can see a lot of other examples. So coming back to the Earth's surface and to social geography, I will now want to add to these preliminary illustrations some images taken from satellites over international borders, across international borders, to illustrate the fact that political borders, strictly political borders, which are not defined by natural elements, can be seen from satellite very, very clearly, very easily. In this first example, we see here in the Western Amazonia, the border between Bolivia and Brazil. And please do not consider this line here, because this is just the limit between 2 images of a mosaic, but rather consider this line, which is really the border. And here, the Bolivian government decided to place here a natural protected area. And while on the same, nearly on the same place, the Brazilian government encouraged extensive agriculture. So we have the same natural area at the beginning, but you can see in this example that the political decisions and the economic reality influence the landscape patterns exactly until the border. Another example, here you can see on the right, this is a rural area of Israel with modern agriculture, and behind the line on the left, you have the Gaza Strip. The Gaza Strip, which is very densely populated. And you can see, just look at the side of the fields, the agricultural fields, you see a very, very great difference between the 2 parts of the image. So if you look at the colors, you see that the vegetation has the same colors, because wheat is wheat, corn is corn, and so on. And you see the same color in the ground, the bare soil, because it's the same geology, the same climate, so that you have no reason for having different characteristics in terms of color. So it means that here only the pattern which has been designed by the human societies on the Earth's surface is due only to political and economical characteristics. So once again, the political decisions and the economic reality expand their influence exactly in terms of landscape pattern exactly until the border. Third and last example of this series, this is the border between the United States on the north and Mexico on the south. And once again, you see that it's not necessary to build a wall to make the border clearly visible from space. And here again, it's not the color, it's only the pattern, the geometric pattern of the landscape, which highlights the difference between the 2 countries. So that once again, the political decisions and the economical reality influence the pattern of the landscape exactly until the border. In these 3 examples, which I took in 3 continents, we see that there is no physical limit at the border. It's the same climate, the same geology, the same soil, and so on. So so that we have originally the same physical landscape. What makes the border clearly visible in the satellite images is that the two territories belong to two different independent countries, where I would say the landscape geometrical pattern are influenced by different legal and economical mechanism, law, real estate economy, but also practices for agriculture, for urbanization, for transport, and so on. So in this example, you can see some natural traces, like here some rivers, but the most impressive, the most important traces are clearly of human origin. However, in some cases, the spatial organization of the territories must adapt to the physical constraints of natural environment, like water and the presence of wetlands and so on, or as illustrated here, the presence of steep slopes, which make create some difficulty for agriculture, example on the left, or urbanization, example on the right. So these two examples are taken in the Mediterranean region for agriculture and urbanization. And we see that the landscape patterns are not exactly produced by the political decision. They are also influenced by the natural reality. Let me show a few examples in which human settlements have tried to avoid the difficulties of natural environment. On the top image, we see the coast of Venezuela on the Caribbean Sea, and we see that the urbanization has saturated the available space and is very totally tight between the sea on the north and a very steep slope mountains on the south, so that it seems to be very densely populated because there is no more space to accept higher demographic pressure. And on the lower image, we have here the coast of French Guiana, and here we see that this coast plain is not suitable for building roads or houses and so on, except just one line which is geologically stable, on which the population is concentrated. In this area, on the north side along the coast, you have a mangrove, which is a forest growing in the sea, which is not suitable at all for human life. And on the south part, on the continental part, there is a wetland which is not suitable for construction and not even for agriculture. So that the only road and the two villages are exactly constructed on this small corridor, which is the only stable, geologically stable line in this area. So in many cases, we can see these strategies to occupy the only the few suitable areas in areas where many natural obstacles do not allow construction. In this example, we have the city of Macapá, which is the capital of the state of Amapá in northern Brazil, Amazonia. And here you can see that there is clearly double influence of nature and society in the design of the landscape patterns. So on the one hand, you have a very regular mechanism of the city design, which is with the orthogonal street and clearly defined by a public authority. But the urban growth, which has begun maybe centuries ago or decades ago, the urban growth suddenly is stopped by the presence of a wetland, and the limit of this wetland is clearly visible in the image. So we have the superposition here of two kinds of geometric patterns, a natural one and an artificial one. And this is the case in many other illustrations, as I will show. And here, in this image of Central America, we can see a city which is trying to expand once again between a very steep mountain and a lake. And I would like to illustrate in a more theoretical way how natural obstacles influence the growth of the city. At the moment, you see that the city has expanded exactly from the lake to the very beginning of the slopes, and that the expansion is continuing on the sides, because here we have a more suitable terrain. So here on the top, the the top drawing here, I illustrate the fact that the city at the moment is growing on the sides, okay, side direction, and we see here recently constructed areas, and we have a higher rate of vegetation because it's not yet very densely urbanized. But what could happen in a few years if the demographic pressure is still very high? What can happen? Maybe not here, but in similar cases, is as I show here below. And first, that people may try to build houses on the slopes or over the water. And in these cases, this is not very good for their health and safety. And they can also continue the propagation of the urban growth, but very, very far from the city. So that's people, we have houses that are likely to be destroyed by nature, or they will live in a suitable environment, but they will have hours and hours of transportation to go to their job every day. And this is often the destiny of poor people in the cities. So that we can see both the urban shape and the social segregation that may appear in the satellite images. Okay, so the last point I would like to mention in this long introduction before I move to remote sensing is the effect of time. The traces of nature and society are left over time, and each trace is written over the previous trace, so that the Earth's surface, I think, can be considered as a palimpsest. What is a palimpsest? It is a very old book, dating back from times when paper was so scarce and expensive that to write a new book, people took an old one and used to erase the writing with a blade in order to be able to reuse the paper. But generally, the old writings still appeared behind the new writing. So a palimpsest is exactly this, a document or a book where we can write, but you can see the writing, but you see the effect of the old writing. And I think this is a good comparison of the Earth's surface, where the new traces are left over all the traces. I would just like to give two examples. Here in French Guiana, we have new traces. We have here riverbank with infrastructures, here a road, here is a new jail. We have here a channel, here another one, and some natural patterns which are written. And this is written over an old writing, old traces. And here we can see an old polder. I think this was a sugar plantation, but this activity stopped during the 18th century. So that during more than 200 years, this was really an old human trace. So that the new writing is written over the older one, more than 2 centuries. And this example is even older because this is from the Gallic civilization. This is a Gallic slide that appears through the Earth's surface. So the present human traces left on the Earth's surface are clearly visible, a motorway, a railway, agricultural fields. But 2,000 years ago here, there was a Gallic city. And once again, the new trace is written over the old trace. So that when we want to analyze satellite images, we often have to separate different periods that are mixed up in the same image. So these few examples until now suggest that traces left on the Earth's surface could provide information on human societies. And since I have just shown a few satellite images, we can expect satellite remote sensing to be, I would say, a relevant tool for social geography. So now, I would like to summarize the different kinds of traces that we can expect to see on the Earth's surface. So among these traces, we will be interested in material traces. I mean, traces that physically exist on the Earth's surface as a transformation. And some of these traces, as already mentioned, are left by nature. And this is an example of a desert area where the wind designed some dunes, some parallel dunes in the desert of Southwest Africa. And other traces, material as well, are left by society. And I just want to show here that some of these traces are planned, some are unplanned. the right example. They are planned. This is the south of Canada, and this is the border with the United States. And the federal government of Canada in the 19th century had a land administration policy with the land sharing with fixed sizes. And then in posterior days, the fields were divided into smaller fields. But you see that this was we have a fixed size and orientation. So this is clearly planned agricultural land geometry. On the other side, here we have something unplanned. This is a suburb in Haiti, a suburb of the capital Port-au-Prince, and clearly the human settlements are not planned when they are previous, when they happen before the planning policy establishment, or when they simply do not obey the planning policy. So all these traces, planned or not planned, natural or human, are visible because they exist on the surface. I'm not saying that all satellites will be able to see them. So I will see later that each satellite may be specialized in the detection of different kinds of traces. But I would like to mention also what I call here ghost traces. I call them ghost traces because the traces do not exist on the surface of the Earth. They are just created by the sensor. The sensor is not perfect. And in this case, I would say that the image is dirty because of the satellite, because of the sensor. Some algorithms exist to clean the images, but they don't work 100% well. And then it's important to know that the images you see on the screen are not perfect. Remember that a few minutes ago, I have shown an image on the border between Bolivia and Brazil. And I told you that do not consider this limit because it's a limit between two images. So this is a ghost trace. You will not see anything on the terrain. So now the principle of remote sensing is quite simple. A sensor is flying over a piece of territory on board a plane or a satellite. And in each position, the sensor will receive some energy, which is light or heat or any other kind of electromagnetic radiation. And this energy coming from the Earth to upwards to the satellite can be either emitted from the Earth, like a heat emission, or also night light. This is emission, or it can be reflected. It can be the solar light reflected by the Earth terrain, or in the case of active sensors like radar, the radar waves is reflected by the Earth's surface and received, an echo is received. So there are different meanings of the light which is received by the sensor. And what is important to understand is that the sensors we are considering, imaging sensor, are designed to organize the different measurements made over a terrain in order to build an image, so that each element of the image, which is called a pixel, is associated with a digital number, which is the intensity of the light received from the corresponding terrain elements. So this is very theoretical. Just a historical background. The first remote sensing image dates back to the Cinque Empire in Paris. The photographer Nadar used a balloon. He flight over Paris in balloon, and this is the first image over Paris. And after the balloon, I want to mention another initiative by a German engineer who used homing pigeons to carry the cameras, and this is the kind of image that they were able to produce. But this was a detail in history, and remote sensing really began with the beginning of aviation, and the remote sensing evolution is really related to the history of aviation. We're really after the First World War, and then of satellites after the 60s. And the first satellite, artificial satellites, was launched with Sputnik, launched in 57, and the first satellite used for remote sensing was in 1960. So the history of remote sensing is really related to the history of aircraft and satellites. And I want also to mention the last kind of platforms used for remote sensing, the most recent, which is the drone or UAV, unmanned aerial vehicle. So it's important to know that after the Second World War, all I think all countries of the world had systematic campaigns of aerial photograph acquisition. So in all continental surfaces are observed with aerial photographs since about 1950. So this is a very interesting source of information. And satellites are systematic. It began in 1972, the first remote sensing satellite as we can use for this kind of application. But I would say that it began in the middle of the 80s with the Landsat 5, as shown on the right, and Spot in France in 1986. So the middle of the 80s is really the beginning of space remote sensing that can be considered as somewhat operational. So in this example, we have two views, 12 years apart, of showing the Amazonian deforestation. Just to show in terms of scale, I would like to say a few words of scales or resolution. It's interesting to note that drone, UAV, brought an intermediate resolution between ground surveying and airborne or spaceborne remote sensing, so that we have a continuum of possibilities from very, very detailed observation with 1 centimeter detail to satellite, which is more likely to produce more regional information. So just to be clear on what I call scale, scale is the same definition as the map, but there is a relationship between scale and resolution. The resolution, as already said, is the ability of the sensor to separate two small targets which are very close to one another, and the resolution is limited by the pixel size. And the pixel size is the size of an element, of a terrain element represented in a pixel. So in this example, number one, we have a low resolution because 1 pixel represents a very large area. And in example 2, we have a high resolution. Now, it's important to understand that high resolution is not necessarily better than low resolution. It just does not show the same thing. For instance, for urban image analysis, low resolution is suitable to show a city, to see the perimeter of a city. High resolution will show a house, a car, a pedestrian, but high resolution will not show a city. So depending on what you want to see, don't believe that high resolution is always better than low resolution, to say nothing about the cost, the higher cost of high resolution. To summarize the improvement over half a century in terms of resolution, I show here two images taken about 50 or 55 years apart. The first decade, which is the 60-70 decade, we had the resolution around 10 kilometers. And the last decade, 2010-2020, we had resolution, as already said, around 1 meter. So there is a ratio of about 10,000 in terms of resolution power between these two generations. So you can see that the change is very spectacular. However, I would like to make some comments based on this double illustration. The first one is that over 50 years, there was no rupture, no breakthrough. I mean, there was no two generation. I don't have two generations. I'm not able to give you a date and to say before this date, it was the first generation, and after the date, it was the second generation, because the evolution, the innovation was continuous and permanent for all aspects technically necessary, optical, orbital, mechanical, computation, and so on. So all techniques necessary to build an Earth observation satellite, there was a continuous evolution for all aspects. So it's something continuous. We don't have a breakthrough in this kind of technologies. The second information is that the improvement has long been related to material, the material put on an orbit, because the way to improve the resolution can be, for instance, to fly it lower. Instead of 1,000 kilometer flight at 250, you will improve the resolution. Another way is to have a wider aperture of the lens and a wider telescope. But if you have a wider telescope, the weight is more important, so there is a cost. And also a very large lens is more likely to break. So there is also a limitation in the size of the lenses. And what I wanted to say is that these limitations related to material aspects, they have been reached already maybe 20 years ago. And now the the more recent improvements are only due to computation. They are only due to algorithms, which the goal of these algorithms is to take the signal, which is typical of the medium resolution image, and to organize the signal in such a way that the resolution is improved. But it's not we improve the results, but not the tool. Another comment, also based on this illustration, that it will not be a very clever idea to improve the resolution permanently every 10 years, for instance, every decade. Because if we want to study environmental evolution, if we want to compare environment today and 20, 30, 40 years ago, we cannot make comparison between these two images. So it's important to keep available some not low but medium resolution images in order to have homogeneous time series, so that we can compare the situation of today and the situation in the past. Finally, a last comment I would like to make is that the image on the right has the same characteristics from satellite as already obtained from aircraft. I mean that some years ago, the satellite was specialized in very large areas and low resolution, and aircraft was specialized in very narrow areas and high resolution. Now, with this kind of images, it's possible now to obtain by satellite the same kind of images, which was exclusively obtained by aircraft maybe 20 or 30 years ago. So it means that for the user, it's not a matter knowing if the image is taken by aircraft or satellite. The only difference is in the possibility to bring the satellite over the area in a given time, but not the characteristic of the image. Okay, so now I would like to show where in the spectral, where in the electromagnetic spectrum we can make some remote sensing. So this scale here is the scale of wavelengths that can exist with light propagation, from 1 nanometer to several kilometers. All this is light. We used to call light the radiation in the visible areas, which is around half a micrometer. But in fact, all this is light. And there are sensors specialized in detecting the light, measuring the light intensity in different spectral domains. And I wanted to show here the three most usual spectral domains in which sensors are being designed and used for remote sensing imagery. First, the optical domain. Optical means that it works like the eye. It's the visible domain plus the beginning of the infrared domain. So this is the measurement of the solar light reflected by Earth's surface, and this is the most usual and also the most intuitive kind of imagery, because it's quite similar to our eye and to our camera. The second spectral domain used for remote sensing is the thermal domain. It is the middle of the infrared, around 10 micrometers, and the images are sensitive to the emission of a heat. Because this kind of wavelength has these characteristics. And if we jump to very long wavelengths, the radio wavelength and the small radio wavelength called microwaves, because they are small radio wave, they are used for radar remote sensing. So a radar, this is well known in the case of for speed monitoring, speed control on the road, but it's also used for some imaging sensors that are able to produce images based on microwave. And I will show later how radar are very sensitive even to human settlements. So each spectral domain is capable of detecting traces of human presence. I saw here the streets in Paris, here a city, and we clearly see that the city emits more intense heat than the countryside. And here we have the Amazonian deforestation seen by the radar. So each spectral domain is sensitive to some traces, characteristic of the human presence, but they don't see exactly the same thing. So I would like to show now the different technologies, the different spectral domains, and to illustrate what they are able to see in some cases. But first of all, I would like to list the criteria. What are the characteristics of the ground surface that should be, in favorable cases, detectable by sensors? The most important one is permanent land cover change. In each point of the Earth's surface, at a given time, we have a characteristics. We have bare soil, we have water, we have the roof of, of buildings, and so on. So when there is a change in permanent land cover, there is a change of maybe color or some other characteristics. And most often, one of the different kind of satellites is able to say that here, for instance, there was some forest and now there is no longer some forest, there is some bare soil. So this is the deforestation, and we can see a change in color from forest to soil. Here, from soil to vegetation. This is the irrigated area in the desert region in Egypt. So here, in this point, there was desert, there was bare soil with no vegetation, and now, thanks to irrigation, there is some vegetation. The satellite, looking at this area before and after the change, is able to describe the change, and we are, in some cases, able to assign this change to a given transformation in terms of human settlement. Other example, from soil to water. Here, there was soil, maybe with some vegetation. This is in the French Alps, and simply creation of artificial light for power production. And here we had soil, and now we have water. The satellite is able to say that this point of the Earth has changed its characteristics from soil to water. And here is the contrary. We had water, and now I don't know exactly if it's soil or concrete. Never mind. There is some change here that the satellite is able to describe. So permanent land cover changes. Another criterion is the existence of some regular patterns that could be typically human. I say typically because it's not necessarily exclusively human, because as I will show in some examples, the nature also is able to create regular patterns. So we have to be careful and not to conclude that the regular pattern is necessarily a human trace. And I will show that there are 2D horizontal patterns, like this orchard, or 3D vertical patterns, like this, the center of a big city. And there are also characteristics that cannot be seen exactly on the ground directly by the satellite, because they are not measured, but they are computed through some models, and I will keep this for next week. So the first one I wanted to mention is optical remote sensing. As I already said, it's the most common one. The wavelength is from 0.4 to 3 micrometers. And in this case, we see the colors of the surface. The colors, which mean that we refer here to the concept of spectral signature. What is the spectral signature? It is the behavior of a given surface, for instance, here vegetation, in terms of reflection as a function of wavelength. It means that for each wavelength, we have here a curve that describes the percentage of light reflected by the vegetation. For instance, in the visible, it's mainly in the green. This is why the vegetation appears green to my eye. And outside the visible, I cannot see this with my eye, but the vegetation is mainly reflective in the infrared. This is the signature of the vegetation. And if I'm able to recognize the signature of some typical surfaces, I can make some interpretation. In terms of visual display, I just want to show that with different wavelengths, we can have natural color. This is possible when the satellites offer blue, green, and red, so that the image reproduces the colors on the ground. But we can have, there are satellites offering green, red, and infrared. And in this case, my screen using blue, green, and red is not able to reproduce the real colors, so that I have false colors. I call them pseudo-natural colors when I represent the infrared in red, so that the vegetation appears green, so that the vegetation appears green, because in this case, it's like a natural color, but it's not, as you can see, it's not the real green as I can observe on the ground. And if I represent, as already shown, I represent the infrared, which is sensitive to vegetation with red channels, then the vegetation will always be red. this example, sorry, tropical rain is making some noise here. In this example, I showed an image in natural colors, which shows that the Amazonian deforestation is characterized by the change in color. Simply, here forest, here agricultural fields, and I also see here a river with a color which is typical from Amazonian rivers, which is like milk or milk with tea or coffee. It's very clear water. Always, also in the optical spectral domain, the night light detection, it consists in observing the Earth's surface at night. And this is an indicator of both population density and the standard of living. In this case, it's obvious that the lights are due to both direct emission from the light and reflection. I mean, the light of the artificial light reflected on the ground and measured by the satellite, so that we have the accumulation of these two phenomena that creates the light, the night lights. Another technology is thermal remote sensing, measurements of radiation between 2 and 5 micrometers and 8 and 15. Why not in between 5 and 8? Because in this interval, the atmosphere is not transparent. It's not possible. It's possible to study the atmosphere, but it's not possible to see the ground surface. So that there are two windows we used to call atmospheric windows, wavelength intervals in which it's possible to see the ground surface. And if I compare an optical image, which is more easy to read, and a thermal image with a color from blue, from dark blue, which is colder, I would say, to red, which is hotter, warmer, then the heat measurement, because this is exactly a heat measurement, is an indicator of two parameters, which are emissivity and temperature. The emissivity is a characteristic of the material. It's characterized the ability of the material to transform heat into radiation, because the satellite only measures radiation. There is no direct measurement of the ground heat, so it's only radiation. Emissivity can change from a material and another, and the temperature can change also, because the storage of heat has modified the temperature, and we can also detect, for instance, default in insulation of houses and so on. There are two reasons for urban surface to increase heat emission. The first one is the replacement of natural materials like water or vegetation by typically mineral materials like concrete. And the second one, in some cases, is heat loss due to heating and air conditioning in the buildings, in the case of poorly insulated buildings. So this is also an application of remote sensing that I will show next time. This is just a comparison between an optical image in natural colors and a thermal image by satellite. Very often, and this is the case here, we don't have we can achieve a better resolution with more finer details in optical imagery than in thermal imagery. And we can see here that the heat emission is more important in urban areas, less important in natural areas, and very low on water. This is typical. Now, radar remote sensing, another technology. I'm moving to microwave from 1 millimeter to 1 meter. Microwaves are interesting because they can work through the atmosphere. The atmosphere is transparent, so you can have clouds and even rain. It can work, and it's an active sensor. It means that the radar transmits a radar wave, a microwave signal to the Earth, and an echo is reflected and brought back to the radar. So it's active. It means that the radar creates its own source of energy so that it can also work at night. So this is called an all-weather sensor because it can work at night and through the rain on the clouds. The radar echo is an indicator of several characteristics that can be meaningful for our topic. The first one is roughness. The radar echo is very sensitive to roughness, because for a reason that I don't have time to explain, the radar emission is always lateral. In this, there is never vertical. And in the case of very smooth surface, the echo, there is no echo. I mean that the whole energy is reflected in the other direction and does not go back to the radar antenna. There is no echo, so that the image is very dark. When the surface is very rough, then there is backscattering, scattering in all direction, and the backscattering is the proportion of energy which is scattered back to the antenna. In this case, there is an echo, and the intensity of this echo leads to an image which may be rather clear. So the intensity of the image may be, in many cases, an indicator of the roughness of the surface. So this is an example of an image where you see a river. Here's the Trans-Amazonian Road in Brazilian Amazonia. This is a river. The water surface is very smooth. These are agricultural fields. So this is the result of deforestation, which is clearly visible here because the surface is smooth for the radar. And here the forest, which is rough for the radar wave. And then we have a clear difference between the forest and the deforested areas. Another illustration of the effect of roughness is that here we have the Mississippi Delta, and here in the Caribbean Sea or the Gulf of Mexico, we have this oil spill. This is petroleum, this is pollution. And why is it dark? Simply because then with some wind, the wind in the surface creates some roughness, which creates this light gray. And the same wind velocity creates less roughness because of the viscosity of the oil. Due to this viscosity, we don't have the same roughness, so that the radar does not identify a rough surface. So radar is a very interesting tool to detect what I previously called ephemeral trace, like oil spill on the sea. The radar echo is also able to detect a very interesting phenomenon for urban remote sensing, which is a phenomenon called double bands. Because when we have a right angle made between a vertical wall and a horizontal street, horizontal ground at least, then the radar wave reflects twice, it's double bands, and comes back to the direction from which it's coming. So that the antenna of the radar will detect a very intense echo. And every time you have some this kind of object, this is an optical image where we see a petrochemical industry with cylindrical tanks, and each tank produces a very, very intense echo, which is easily to detect for radar. Here in the urban area, we have an example. This is the city of Rome with a low resolution radar area, and here a high resolution with a river, bridges, buildings, boats, and so on. And in both cases, we can see that each pixel in which there is the presence of a vertical right angle, then there is a very bright intensity in the image. So this can be a criterion as well to recognize areas where some constructions are present on the surface of the Earth. And another information that can be obtained from the radar echo is the surface stability. It will be too complex to explain this technique. I just want to give his name. It's called interferometry. Interferometry consists in taking two radar images and compare them with the specific algorithms with two main applications. One is to create topographic maps in stereo between the two images. And the other one is when the two images are taken at different dates, is to detect some small subsidence. Small, it means centimetric. And here, for instance, what the so-called radar interferogram show that each strip here is half the wavelength of the radar, which is about 3 centimeters. So this is the result of an earthquake a few years ago. And this image was used by geologists to analyze what happened exactly between before and after the earthquake in terms of earth deformation. And this is not what I'm wanting to measure, to comment on today. I wanted to show that this technique can be polluted by some noise here. There is some noise in the image, which is due to the presence of unstable surfaces. Unstable maybe vegetation of water. It means that between the two dates, the radar will not see exactly the same distribution of small objects comparable with the radar wavelength, I mean at centimetric scale. So the radar, with this sensitivity to irregular movement on the surface is able to distinguish between unstable surface and a stable surface. And the level of noise can be measured, computed, and it's possible to create what is called the coherence image. And this is an example of a coherence image. In the bright pixels are pixels which show stable surfaces, agricultural fields with no vegetation in winter, for instance. And the dark pixels show here a lake, because this is typically unstable. This is a river, water. This is forest. And some agricultural fields have vegetation which is unstable between the 2 days or over a few days. So this is also an information that can, a measurement that can give me some information, thanks to the radar image, on surface stability. And as you see, I can clearly distinguish between forest and city. Other criterion is the presence of regular pattern. I can show here 2 examples. On the top line, hydrography. So here I can see the natural hydrography in terms of river geometry, and artificial ones in urban areas are very different geometric patterns. So this can be a criterion to identify human traces, and also urbanization, because the urbanization always obeys, as shown in the introductory illustrations, always obeys some patterns. And I will show that I can see the difference between a city center here, residential area with planned urbanization, and here an unplanned urbanization with people have built houses with no authorization. I would like to show through this illustration that horizontal patterns are not necessarily exclusive from human traces. On the left, you have Amazonian deforestation with clearly regular patterns, which are clearly planned. And on the right, an example already shown of parallel dunes in the desert. So don't believe that parallel lines are necessarily of human origin. And vertical patterns can also be seen on the surface of the Earth, so that in this case, one satellite image is not able to give me some vertical patterns. I need to implement some specific techniques. Apart from radar double bonds that I already mentioned, I need to implement specific techniques for 3D mapping. And the main ones are airborne LiDAR, which is a laser on board plane, an aircraft or satellite, sending laser pulses, and the echo received after the reflection of the Earth is used to measure the time, the propagation time between emission and reception, and this gives me a point which is perfectly located due to this distance measurement. So this gives point clouds that are used to map the Earth's surface. And the other technique, which is more ancient, is photogrammetry, which uses photographs acquired in a stereoscopic configuration between 2 positions of an aircraft or a satellite in order to derive a 3D model. And in both cases, it's very important. There are some technical constraints, like the measurement at any time of the position and the orientation of the platform carrying on board the sensor. So these vertical patterns can be revealed in the 3D maps. For instance, photogrammetry nowadays is widely used to build urban models. Here, this is widely used in the internet if you want to surf to see your home. And in this case, we can distinguish between different kinds of objects in terms of vertical shape. And I also wanted to show that airborne LiDAR is able to reveal vertical shape, 3D artificial shapes, even through a dense rainforest. So this is an example in Central America, where you can see the traces of past civilization, of the Maya civilization, and it's totally invisible in aerial photographs or even on the ground, because there is a low, dense, low vegetation. So it's not possible to see them without a specific techniques, and airborne LiDAR is able, due to this, the way it works, sending laser pulses. The laser pulse is so thin that it's able to not to cross the leaves, but to pass through the leaves in the holes, and just even it's so dense that even a few % of the pulses reaching the ground are able, by an interpolation process of the surface, are able to describe the ground. For your information, this is the only technique nowadays which is used in, I would say, industrially, to produce topographic maps through forests. So this is a way to describe not only archaeological infrastructure, but any kind of human infrastructure that could be seen, that we could want to see through the forest. Now, a question. Many in the literature do know that many poets have noted the beauty of irregular structures in nature and rejected the human structures filled with right angles. So I would like to show that this is not so simple. Is that and the question, is the right angle exclusive of human constructions, is not so simple. I want to show that first of all, the right angle can be considered in the horizontal dimension or in the vertical dimension. The horizontal right angle, we can facilitate the sharing of land and the practical organization of cities. This is true that if you take, I don't know if I can do this with my camera. If I take a piece of paper and I fold the paper once in one dimension and then in the second one. So if I open it, here I have exactly a right angle in the center. So it's somewhat natural in, I would say, in arithmetic terms, because if we consider the whole plane, if you divide the plane in an integer number of parts by 2, 3, 4, and so on, then the right angle is something very intuitive when you share the land between different owners. So this is why in many civilizations, from beginning with the Romans in Europe and typically in the 2 American continents, we have almost everywhere some land administration planning making wide use of horizontal right angles. So if you look at this kind of geometry, we can almost always say that it's typical of human presence, because I'm not used of seeing in nature this kind of traits with systematic use of right angles. On the left, it's a city in Brazil, and on the right, it's agricultural fields in Canada. As already shown, there is a land administration, an old land administration planning with a very clearly defined shape and size. Now, considering vertical right angle, it's not so clear that it's typical of the human presence, because the vertical right angle is the angle that allows the stability of buildings. Very high buildings are all vertical. Sometimes they have a very strange shape. They are turning around an axe and so on, but they are vertical. It means that the top floor is exactly above the ground floor. And why is it vertical? Because it's the angle that allows the stability. Nobody would try to build a very, very high building in inclined orientation, because it will fall very, very quickly. And if you look at nature, the right angle is exactly the angle between the vertical, which is the natural direction of gravity, the vertical line. This is something natural. And the horizontal surface, which is also something very natural, because it is the surface of it's the orientation of the water surface. So if you drop a small stone over a water surface, the impact of this stone on the water is exactly a right angle, and you decided nothing as a human. So I can say that the vertical right angle is very present in nature, and the best example, which is somewhat comparable to high buildings, is the tree. Why are trees vertical or almost often, very often vertical? Because this is the stability angle. A tree which is not vertical is not so stable, is more likely to fall. And the other reason in nature is the vertical direction for a tree, for the tree growth, is that is the direction that allows the tree to get quicker at the top of the forest to get some light for its growth, okay, for its life. So I cannot say that vertical right angle is typical of human presence. So to answer the initial question, is the right angle exclusive of human construction? If you look for right angle as a criteria for human settlements, look for horizontal right angles, and okay, you will have some typical criterion of human presence. And if you look at now at the vertical right angle, it's not necessarily the case. Okay. Now I just remembering that I forget to mention a detail in the previous slide. Sorry for this. Yes, when I was referring to resolution, here I refer to scale and resolution, and then I spoke of the spectral domain. In fact, in each spectral domain, we may have different resolution. We have visible images with high and low resolution, infrared images with high and low resolution, and microwave images with high and low resolution. And we will not detect the same thing. For instance, in radar imagery, in the high resolution, I can detect each object. I can detect a bridge, I can detect a building, I can detect a boat, and so on. So each object has a response. But in low imagery, I can only say that I have a higher concentration of vertical right angle, and this is the fact that I just spoke of vertical right angle made me remember of this detail. I only have a high concentration of vertical right angles in one radar pixel, so that the reasoning of the photo interpretation is not exactly the same for low resolution and for high resolution. And similarly, in optical images, for instance, here I can have a very when I say that some traces were planned and some traces were not planned, here in this example, you see that here we have two parallel lines and even three parallel lines. So in this case, it's clear that at this scale, the human settlement is planned. But if we look closer, and I did not prepare a zoom for this slide, if we look closer, it's a mess here. It's very, almost a random organization of the parcel. But there is a force, there is an attraction of the road, because if I have an agricultural parcel, I need to be close to a road because I need the road to transport my harvest, my production, so that nobody likes to settle agricultural parcel very far from the road. So that we had an attractor, which is the road, which has been planned with land surveyors paid by a government, state or federal government. And with this road being built with public money, people, there is a private market to access the landfills. So we have a clear planning of the spatial organization of the human settlement, and unplanned settlement if we look closer. So at the different scales, we can have something planned at a low resolution and unplanned at high resolution, or sometimes the contrary, we can have something unplanned. I'm not sure if I have the illustration here for this. We may have something unplanned at low resolution because there are mountains, there are rivers, there are different natural obstacles, and it can be planned at a higher resolution. And in fact, yes, I think I have the illustration of this. It was here. Oops, I'm sorry for this, for coming back. Here, I have something at low resolution. I will clearly see the limit of this wetland. So I have something which is not planned, either because it's natural or because it's of human origin, but with no planning mechanism. And at a higher resolution, I will see the limits of the position of the streets, which were clearly defined by the public administration. Okay, and if I zoom again at a very, very high resolution, what I will see the freedom of each citizen to have proper garden, houses of different sizes, garden. My garden is very well organized. My neighbor's garden is a mess. So at another scale, I will see some heterogeneity of unplanned kind again. Okay, so I spoke of scale, which is an important criterion to know that we don't see the same thing at different scales or different resolutions. I spoke of the spectral domain, because satellites working in different spectral domains will not see the same thing. But in fact, in the interpretation of each image, we will see different things at different resolution. And only this example shows that we have something which is disorder at low resolution, order at medium resolution, and disorder again at higher resolution. Okay, so that this is important it's important to be careful when transferring information from one scale to another scale. Okay, so I'll go back to my presentation, but I think I was coming to the end of my presentation, because I want to leave some 15 minutes for some question or comments. So I'm sorry for coming back now, but okay. So this was the final question, and I show that you've seen that I'm referring to here the third category of criterion, which is not directly measured by the satellite, but computed through models. So the satellite measurement is converted through a mathematical model into parameters, and I will give the example of demographic density, which is an environmental parameter, social in this case. But I wanted to take this to the next presentation next week, because I will show some information about different initiatives that have been published in terms of demographic mapping with satellite images using different wavelengths. So that this first part, really, I wanted to show the great variety of sensors which do not see the same thing and which are able to see different traces on the Earth's surface. And I kept from next week some applications in which I was personally involved or taken from some publications found in the literature, to show that these methods can be applied to answer some scientific or operational questions. And I will try to show as well that there is some limitation, and that in spite of the great potential of satellite imagery to show some traces, and through these traces to reveal some information about human societies, I will show that in spite of this potential, it's not always easy, and sometimes there are errors that can be made in this kind of interpretation. So this was just to conclude this first part, and I wanted to keep a few 10-15 minutes to questions. So I don't know if some questions appeared on the chat while I was speaking, or if some person can.
Yeah, thank you, Laurent. This is great. So we have 20 minutes for questions. Could I take the privilege to ask a first question?
Sure.
Yeah. So you were talking, I wanted to move back to your image of the spectra, because you show that at least it seems easier to detect changes in vegetation than in water, because water was more stable. So I was wondering if you could talk more about the possibilities to detect water depth or water pollution in the form of algae bloom. You gave the example of oil pollution. It was very clear. You could see that through a radar image, I think. But because it's true that I think we know more about Landsat for deforestation and so on for vegetation. But for water, I would be interested if you could talk a bit.
So when you see water, I can take any example here. We have an example, or I have many examples with water. Sorry, just to take one. Just when water here on the top. When you see water in satellite imagery, in remote sensing imagery, you can see three things, or part of three things. One is the color of the surface. What happens on the surface? You can have surface pollution, for instance. You can have waves on the surface. The second thing you can see is the volume, inside the water, between the surface and the bottom. So in some cases, when there is some pollution inside the water, in some cases you can see it. And the third thing is the bottom. When the water is very clear and not very deep, in some cases optical imagery can show the bottom, and you can see something in the bottom. Generally, when for a given sensor, when the surface can hide the volume, and the volume can hide the bottom. So when I mention these three kinds of influences, it's the maximum you can see, but very often you can see only one of them. You can not see the volume if the water is very clear. It's totally transparent, so you see only the bottom. If there is some sun glint on the surface, you can see some. I don't have example here, but you will see some bright pixels due to the sun glint. So each pixel over water is a potential mixture of the three potential causes. But you have to be careful because very often you will see only one. Concerning the radar does not see through the surface. The radar wave is not able to penetrate. It penetrates maybe 0.5 millimeter, so you can neglect this penetration depth. So it's only the radar can see two possible things that have been seen on my slide. First, the roughness. Here you can see the water. It's very smooth. So when it's dark, it's because it's a very smooth surface compared to the land, which is very rough. And the other thing you can see is here roughness too, because the pollution is very smoother than the clean water. And the other thing you can see is the fact that water is unstable. The water moves permanently. So here you have a low coherence. This product is called coherence. It's built jointly with the interferogram, which is used to subsidence mapping and so on. We can at the same time produce a coherence image to see the stability, the stability of the surface. So if we consider that the water is both smooth and unstable, then we have a double information from the radar imagery. But among the three kinds of information that remote sensing can access, as mentioned previously, the radar is only able to see the surface. Maybe I will try not to forget it. I will show in the presentation of next week that the radar is able to see indirectly the bottom, because in the presence of a buried object like a sandbank or a mud bank, there is a small roughness on the surface, and the radar is, as I already said, the radar is only able to see the surface and can see the impact on the surface of the presence of a submarine or mud bank and so on. So the information is very rich, but you have to know a little about the physical behavior of the sensor.
But then it means you can detect objects which are not too deep, basically, into the water. Yes. You can't differentiate if there is the Titanic.
Yes, no, Titanic, you will not be able to detect it. You need a sonar, which is an acoustic sensor on board the boat. But the radar, for geology in shallow water areas, it's interesting. And the radar imagery has been used to put telephone cables between England and France, to look for valleys in the bottom of the channel, because it's not very deep. just a few tens of meters.
Okay, but yeah, it goes up to a few tens of meters. Like it's
yes,
not,
but no more, not hundreds, only tens, a few tens, and it depends on the current, because if there is no current, there is no impact on the surface. But in the river, for instance, in the river, if there is a stone, a very big stone, very close to the surface, which is dangerous for navigation, there is always some agitation of the water over this stone, which is the people who drive a boat. They know exactly how to recognize this kind of obstacle. And the radar is similarly, the radar is with another wavelength is able to see the same effect, which is the effect of the presence of the objects a few meters typically, and until a few tens of meters.
So maybe as we are talking about objects which are a bit hidden, like on the picture you were showing, like in the Latin American rainforest, where we see like former human settlements.
Yes.
So I suppose, so here basically it means that using one wavelength you can have an idea of how tall are the trees, like, or big are the trees. And if you use the other wavelength, then you can get information on what is behind the tree, so you can get precise information on the biomass which is above ground, or is it?
Well, in this case, it's an optical. I spoke of the different wavelengths for the measurement of the intensity of the radiation, and I spoke of optical, thermal, and radar imagery. Here, when I spoke of vertical patterns, I spoke of two techniques, which are LiDAR, airborne LiDAR, and photogrammetry. And in this case, the product is pure geometry. So there is a signal with a specific wavelength, and this signal is able to penetrate or not, and so on. But the product we obtain is pure geometry. I mean that this technique is able or not to locate a point in 3D on the Earth's surface. And in the case of LiDAR, maybe 90 or 95 or 99% of the points which are sensed by the laser are over the canopy or inside the canopy in the foliage. And a few of them, maybe 1%, a few of them, maybe 1% of the pulses are able to find, are lucky enough to find a hole between the leaves and to reach the ground and be reflected. Sometimes they're reflected by a branch at 2 meters over the ground, so that there will be you will make an error. If you make an error, if you think it's the ground. So in this case, we have a point cloud, and in this cloud, only a few of these points are on the ground. But if the plane is flying very low and very slow, you will have a very high density of the point cloud, so that you can remove 99%. Which are not interesting for this application. You can use to evaluate biomass and so on, but for archaeology or topography, you will keep only 1%. You will filter all the leaves and the branches, and you keep only the lowest points. And interpolating between points to generate a surface, you can create a topographic map. And in some cases, the topographic map is as beautiful as this one, revealing some human presence that were not suspected during the last 500 years.
Okay.
We got a question on the chat.
Okay.
Yeah, okay. From Sandrine Mesflé-Soms. I don't know if you want your micro activated. Otherwise, I can start. Okay. Yeah, great.
Thanks for this presentation and this masterclass. Thanks for giving the floor. Yes, I have perhaps a stupid question. I would like to know to what extent the technique using the difference in temperature works in zone like Africa with the hot temperature to identify areas where there are inhabitants. And more generally, I would like to know which technique works the best, or which technique are the most available in Africa, knowing that for me, I'm quite a bit skeptical about the suitability of the light night data to be able to measure correctly GDP or inhabitants in Africa. Thanks a lot.
Well, I would not say that light night is not suitable. I would just say that there is no light night in some places, so that you can conclude that there is either a low density of population or a low standard of living. So in many cases in Africa, this is the case. It's also the case in other parts of the world. When you have a desert, it's not the same explanation that when you have many people, but just people who cannot afford to have light switched on all over the night. So I think this is the main first answer you can have. Now, I agree that night light is very limited. I will show next week that some application for demography, but you have to calibrate. You have to calibrate. I mean that in this mixture of influences of demographic density and standard of living, you have to calibrate the interaction between the two influences. And if the standard of living is too low, it's impossible to make some conclusion. And in this sense, I can say that you are right. And it's necessary to mix these techniques with, or to substitute these techniques with others, and to work with other techniques as I have mentioned. I hope you believe at least in some other techniques I've shown. But I wanted to say that there is no stupid question. Don't worry about this.
And other questions?
Yes, so maybe I jump in with a question about like resolution. So like as economists, we tend to use like very large samples, which means that we tend to try to cover relatively big chunks of landscape, so it pushes us towards like high resolution. On the other side, towards low resolution. On the other side, of course, we tend to look for precision, and so it would push us towards high resolution over big landscapes, which then becomes computationally very intensive. But so where should we place this trade-off? Like my usual sense of the trade-off is that we should not try to have a better resolution in terms of remote sensing than the resolution we have in terms of socioeconomic data. But maybe you have a better insight of like the trade-off between high and low resolution in this kind of context where we try to cover a whole country or.
Okay, well, it's not so simple to answer, because in fact it's not a trade-off; it's a multiple trade-off, because there are several issues leading to trade-off in different dimensions. For instance, the cost. High resolution is a square kilometer is very costly. I'm not speaking of money, I'm speaking of technological cost, and because the resolution has some drawbacks. If you want to improve the resolution, you have to forget some other requirements. One of them, which is very important, that I will mention next week, is that high resolution is you lose the temporal frequency. For instance, if you want to see every day, it's not possible to have a very high resolution. You have to wait for several days or weeks or months. And then if you want to see every day, unfortunately, you have to accept a lower resolution. This is just an example, and there are a lot of relationship, a lot of trade-off, as you said, between resolution and some other aspects. Now, speaking as a resolution as a criterion to purely spatial criteria, and forgetting the cost and the time dimension and so on. As I said, well, it was very general sentence when I said that high and low resolution don't see the same thing. So it's very important to understand that the information is quite different. It's not high resolution does not improve the possibility of detecting something. You can lose some information which is only visible for at low resolution. And referring to sample size, this is important too. If you have high resolution, you may have many pixels, and then you have many samples. So you have a good sample size with many pixels, but each pixel is poor in terms of information. On the contrary, you can have a few large pixels, so it seems that your sample size is small, but each pixel itself is a large sample because it integrates many things, many houses, many trees, and so on. So you also have a trade-off in terms of sample size between high resolution and low resolution, which can allow large samples on two different ways. I don't know if this answer is meaningful for your question. But I will show next week some illustrations of this trade-off, and your question is just an anticipation of what I will show Monday, because this sensitivity of different sensors can be used to make land use maps, and land use change typically can be mapped. You can publish a land use map before and after, let's say at 2 dates, and then the samples you use for training the algorithms to produce a whole map, the sample is very, very important. And so your question is very relevant in that sense.
We have 2 more questions on the chat, if I may. The first one is from Jeremy Gignoux. Can you provide more details on the methods and signals used to sense different crops? Can we today tell what crops are grown just by looking at satellite data?
Okay. The first level is I would say, a detection level. I saw spectral signature, which is the curve that describes the way one given crop behaves with regards to lights in different wavelengths. So this is the first things that can be used to discriminate different crops, and to discriminate for the same crop different stages, or the presence of a disease or lack of water and different problems. So the color, I would say the color is spectral signature, means somewhat color, is an information about what crop do I have in this parcel, and is there some problem with this crop, and so on. And more sophisticated levels is a level that use modeling. Some crops are so well known that we are able to write mathematical equations to describe for instance, for sunflower, tournesol, which is a flower that produces oil. There are some mathematical equations that relate the quantity of oil that you can expect at the end of the agricultural seasons with some parameters, the height, the weight of the leaves, the weight of the flower, some parameter that can be observed 2 months before the harvest. Exactly like when you have an ecography of a baby before the birth, you can relate the length of the arm with the weight after the birth. So there are some empirical relationship that can be written through mathematical equations. And then when you have a few images over different crops, you can measure some, you can relate some measurements that we make today with the quantity with the harvest you can expect, and also to the date, the probable date of the harvest. So this is very widely used. I'm not the best specialist of this, but the images are used to be the data are fit on theoretical models in order to project your knowledge to later dates in order to know what is going to happen with your harvest.
So it's mainly for some crops then, some specific crops that it works better.
To predict crops, but you have to know, you need to know the crops quite well. So this is used for crop prediction. I know that this has often been used for speculation, because when you know before the others the quality of the crops and the quantity of the crops, maybe you can act on the market. So that and there are some initiatives to try to use satellite imagery to create some transparency in order to avoid people to speculate by knowing before the others about the harvest.
Then a last question maybe from Mélanie Gittard. I don't know if you want to deactivate your micro or if you can.
Yeah, thank you.
Okay.
Hi. But it was just a question because to know whether next week we're going to talk about rainfall projects, data that are like driven from satellite images or remote sensing. Are we going to talk about that or not?
I don't understand. I don't understand the
like
beginning
more
of the
about rainfall projects and data that are like driven from remote sensing and satellite imageries. And I mean, are we going to talk about that next week or?
I missed a word. I missed a word at the beginning of your sentence. I'm sorry. The key word of the whole question.
Rainfall projects.
Okay. Rainfall
projects.
Well, I can show something, but it will be very limited. Huh? My expertise is really on the ground, and or climatic and meteorological aspects are not really my
Okay. But maybe I have a question about just the question of Jeremy, just about that, because is it very hard to distinguish different types of biomass, like for example, trees from herbs, or is it something that we can do? Like
between different?
Like herbs and trees, for example, different types of biomass.
Of vegetables.
Yes.
I've oriented my presentation to distinguish human traces, but I could make exactly the same presentation to discriminate different types of vegetables. It's exactly the same behavior, the same way. You need to look for some criteria in terms of color. It's not the same color because if you cut the forest to put a crop, it's not the same biological phenomenon. The photosynthesis will not act in the same way, so that you will not have the same color, and some sensor will see it. It's not the same roughness, the radar will see it. It's not the same height, because the trees are 30 meters height and the coron is only 2 meters. So photogrammetry and airborne radar will see it. So you can apply more or less the same program as I've just shown, as how first list the different sensors and think of the different possible scales, special scales, and look at what each sensor is able to see. So the answer is yes, clearly, but because there are many criteria, spatial patterns and physical response and so on.
Okay, thank you.
Okay, great. Anyone else? Or maybe it's time to wrap up. You're very generous with your time, Laurent. So just to remind everyone, this is just the first part. We've broken it into 2 pieces because of the Zoom constraint. So I hope to see all of you. I mean, we do hope to see all of you Monday, the 8th of March at the same time, 3:30.
Is it the same link?
It's the same link.
Okay.
Indeed. You can keep the same link.
Okay.
You will make some room too for discussion and questions.
Yes.
So thank you everyone for attending, and thank you, Laurent, for this very stimulating talk.